Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we're going to be beginning our three-lecture detour into computational chemistry methods, which, as many of you know, is kind of my specialty, and I do love them. So we're going to focus a little bit less on how to use these computational methods and more on kind of the hardware equations that are going behind these computational methods. And specifically, I want you to pay attention to the strengths and weaknesses of the various methods we're going to be talking about. So today we're going to be starting off with the simplest set of methods called semi-empirical methods. These are referred to as semi-empirical because a fair number of their parameters and equations actually come from empirical fittings, so from experimental data. So these are not what are called ab initio or first principle methods. As such, they're often sneered out by many, and you'll kind of see why there is some support for the degrading of semi-empirical methods. So the basic idea with semi-empirical methods is actually we start straight from where we were looking at last time, playing around with our secular equations. So we're going to build up a nice big matrix based on all of the atomic orbitals involved. And now what we have to then pay attention to is our Coulombic integrals, which are essentially the interaction of an orbital with itself. So these are going to be along the diagonal elements. The resonance integrals, so these are going to be the off-diagonal elements where I've got the interaction between two different orbitals. And then finally, the overlap integrals. So this is essentially how much does an orbital overlap or interact with another orbital. Higher the overlap, more interaction, and thus we're going to have actual electrons that exist in this overlap region, which will largely dictate bonding and anti-bonding character. So we have a known way to try and describe these molecular systems, but the problem is that, as you've seen, a lot of these equations start becoming really hefty to deal with. So the key trick to a computational method is going to be trying to simplify these methods, and we're going to focus on two main issues. First of all, we're going to try and simplify the matrix by pre-solving terms. So if I don't have to actually compute the resonance Coulombic or overlap integrals, this is going to make all of my equations go a lot faster because at that point, all I have to worry about is simply the linear algebra, which by no means is still easy. And one of the reasons why even the simplest computational method takes a fair amount of time to try and solve. The other key point that we're going to spend a lot of time on is trying to determine the best form of the Hamiltonian. Because if I know the form of my Hamiltonian, this should hopefully give me a quicker way to try and solve any Coulombic or resonance integrals that I can't just put in a known value. And really, any computational method we look at is going to be defined by these two key features. How do I simplify this matrix? And what Hamiltonian I use. So again, easiest form is called the semi-empirical method. So they use a series of approximations. And we're going to focus by first looking at these overlapped integrals. So there's a lot of different semi-empirical methods, but these simplest methods, these are often quick analysis methods, not the ones most commonly used, take a fairly simple approach, and the same one we use with Huckel theory. I simply set my overlap integral to a Kronecker delta. So if the orbitals interacting are identical, so my diagonal elements, my overlap integral is 1. If I'm looking at the interaction between two different orbitals, so any of my off-diagonal elements, the value is 0. And as we saw previously, this really helps simplify the description of the matrix, because then all I need to do, take a simple set of eigenvalues and eigenfunctions. Unfortunately, this gives us fairly poor results, as we've seen previously. So if you want anything more than a qualitative description, you're going to probably want to use a semi-empirical method such as AM1 or PM3. So what they do is they tend to try and use a lot of pre-solved expressions for these overlap integrals. So what they do is they first of all look at which types of orbitals are involved, S, P, or D, and then simply use the distance in between the two atoms to quickly try and figure out what the overlap integral is. And to a certain extent, this is fairly similar to what we did with simple molecular orbital theory and LCAO methods. So essentially, it's a slightly more advanced version of this and allows these overlap integrals to be quickly determined. However, that still leaves us with the peskier problem of these terms involving the Hamiltonian. So the easiest one is almost always going to be the Coulombic integral. So these are the matrix elements along the diagonal. And so in most cases, we tend to fit these to experimental data. So the experimental data that we chose to use previously is going to be the electronegativity values. So again, the electronegativity of all of our orbitals are fairly well-known features and provide a pretty good starting point. However, as we go to more advanced methods like AM1 and PM3, what we tend to do is we use these electronegativities as a starting point, and then we correct these using a series of pre-parameterized interactions of these orbitals with all the surrounding electrons. So you can imagine if I've got more surrounding valence electrons, I would expect a repulsive feature, so for my orbitals to collapse. If I've got more attractive features, I'd expect them to expand as they try and interact with other nuclei. So knowing the other, what other nuclei and atomic orbitals are nearby can essentially help us correct these energies a little bit and further improve our values. However, the real pesky feature is what is called our resonance integrals. So these are the off-diagonal elements. And these are also solved with a series of pre-solved variables. So the first part that we start with is that these resonance integrals can be given by essentially an average of these beta parameters, which are essentially going to be parameterized resonance integrals. So every single atom, every single different type of atom will have its own tendency of overlapping with adjacent systems. And so I can simply take the average of the two atoms interacting and then correct this based on the extent of overlap. So most of the actual electronic properties given by a specific molecule, so for example, any dependence on the radii, the distance in between the two atoms, is entirely isolated in the overlap integral. However, the second term is a little bit more finicky. So the second term, essentially what it does is it prevents any double counting of electron interactions. Because you can imagine if I'm looking at the interaction in between two different orbitals, well, I may have a little bit of character cross-linked in their interactions with all the surrounding systems. And this is often called electron exchange. And we're going to talk about it a little bit more next time as we get into Hartree-Fock theory, because this becomes a dominant portion of Hartree-Fock theory, essentially this description of resonance integrals. And it's going to share a lot of features with semi-empirical methods, but without quite so many shortcuts. So in summary, semi-empirical methods are most famous because they are very, very fast. These methods, with most of the integrals already being pre-solved, are about as quick as any quantum mechanical method will get. However, you'll notice that we take a lot of shortcuts, and these shortcuts, well, they tend to give us energies that are qualitatively correct, but in terms of real quantitative analysis, you only tend to get good answers if you're working in a system that's very similar to the systems that were originally parameterized. So if these parameters were originally taken for, say, a small organic system, semi-empirical will do okay on small organic systems. However, the more different your system is from the one that was originally used to parameterize the semi-empirical method you're using, the less accurate you'll be. So for true reliability, we're often going to need a more advanced method. So next time, we're going to focus a little bit more on Hartree-Fock. It's probably the first widely used, fairly universal computational method. So until next time, take care.